So in terms of powder, some of the systems that we have worked with commonly include ceramics, but we've done some work with some metal powders as well. And we have worked with some polymer powders as well. CNXL is cellulose nanocrystal. And TYMV are it's turnip yellow mosaic virus. So in turnip leaves, turnip is a vegetable. In the leaves, sometimes you will have some discoloration. The discoloration is from some virus. The virus has perfect spheres. Virus has a protein shell and it has an RNA inside. If you boil the virus, the protein shell remains, but the RNA goes away, and so now it is just an empty sphere, hollow sphere, which is about 30 nanometers in size, naturally occurring. And so some interesting shapes. So we've done some work with that. In terms of patterns, we've tried to create these kinds of structures with silver, gold, aluminum on either silicon, glass, indium tin oxide, and also on polymers. SU8 is an epoxy, PMMA is plexiglass. So transparent materials on which these kinds of patterns are created, and we were interested in some kinds of interesting optical properties of such materials called metamaterials. You can see that roughly the width of the rod is about 50 nanometers or something like that. The length of it is a couple of maybe it's something like about almost 400 nanometers. The spacing between the rods in this case is also about close to 350 to 400 nanometers. So how to be able to create these kind of structures on a now a few 10 micron by 10 micron area, for instance, right? And what use can they have? In terms of pores, we looked at pores in terms of alumina by anodization. We looked at some work with titanium in terms of just sintered particles. And then finally, we looked at polysulfone, which is a polymer, and we tried to create nanoscale pores with that as well. So powders, patterns, pores, all in the nanostructured regime. How to be able to work with something like that. Of course, the stainless steels, we did not work with nanoscale materials, but we did work with some of the palladium, silver, and gold nanoparticles as composites. So the main theme of my research, this is our research building at the background, but the main theme of our research is how to take different kinds of these nanostructures, different patterns, put them into systems which have microstructures. Okay, so channels, we saw a lot of that example when we were trying to look at injection molding of such features. I'll show you some examples of some some microscale wells as well, made from nanoparticles, and some pillars in some cases. The applications in which we are trying to combine nanomaterials and micro features include healthcare. So that particular microchannel plate that you see is the starting point for a portable kidney dialysis machine. And they have microscale features which are about like between 100 microns to about a couple of hundred microns. And the membrane that we made is a powder polymer composite, cellulose nanocrystals, which are hydrophilic, and in a polysulfone matrix where polysulfone is blood compatible. So you can look at kidney as a filter, right? You have water and you have toxic materials. The toxic materials have to pass through and so out of the body, right? And when the kidney is not functioning correctly, that filtration does not occur well, right? Dialysis is the method by which you treat kidney malfunction. And the current way to do that is you wait for a chance to get onto the machine in a hospital. The size of the machine might be about this big, like a refrigerator roughly. And because it's a large machine and there are limited machines, the blood is passed through the dialyzer at a much higher flow rate than in the body. Because of that, first of all, you go through dialysis because your body is full of toxic materials that are not coming out, and so you're sick. Now, when you filter the blood at a very fast rate, there's a lot of damage to the blood, and the body cannot handle the shock of a high flow rate of blood. And that is necessary because there are few machines, and so the filtration has to occur fast because there are a lot of people waiting to get dialysis treatment. So what we have tried to look at with the microchannel structures is be able to miniaturize this to a unit that's about the size of this. And so what that means is now you can have a lot of small machines that people can either wear, or they can go to either in their home itself. They can go ahead and have the treatment at a slower rate, and so their health is in a better condition. And because it's a small enough machine, right, you can go ahead and make that inexpensively. You don't need a giant machine. And so that is the technology that I indicated to you a couple of classes ago when we were looking at different processes. That in building that, we filed for a patent. The patent was licensed to a company. The company received about $50 million in private investment to be able to just do the clinical trials, to test to see how it works and to be able to make modifications. So it's not yet out in the market, but it's in the clinical trial stage. And the membranes that are used for filtering are made by a, a combination of powder and polymer, cellulose nanoparticles in a membrane, in a polysulfone matrix. Mainly, the cellulose nanoparticles are high aspect ratio. They're long. They're about 20 to 50 nanometers in diameter and about half micron to 1 micron in length. So they're needle-like. They're also hydrophilic and they're biocompatible. When we put this in a membrane, the membrane becomes stiff. That is, the instead of you want to have a very thin membrane. You want to reduce the thickness. Membrane is just a sheet of paper you can think of with a lot of pores in it, right? It is used for filtering. So toxins go out and on one side, and then the purified blood, right? So what you have is you have water flowing on one side, you have blood flowing on the other side of the membrane, okay? And the toxins from the blood diffuse into the water, and that's flushed out. The purified blood is put back into the patient, right? The thinner the membrane, the faster the diffusion of the toxins from the blood to the water, right? But the thinner the membrane, as you can imagine, right, the weaker the membrane structure, it can fold over very easily, right? So you can put fillers to increase the stiffness of anything, right? But when you put fillers in there, powders, they can block flow, right? And so you want stiffness, but you don't want to block flow. You want permeability on the one hand, and you also want to have stiffness. And so the cellulose nanoparticles allow to do that. And so it turned out that this is a good combination to try to do that. We also looked at sensors. I'll give you some idea of how to take nanoparticles, incorporate them into sensors, both chemical sensors and for biosensors. And we've seen some packaging applications earlier on, and I'll show you some examples related to that. And then it builds on from there into some energy applications and so on. Okay? Yes. Maybe in the future. Um, Recently, probably earlier this week, there was a news article. So there was a small child using stem cell treatment, had his windpipe recreated using stem cells. That stem cells, now what happened was, as a baby, the windpipe was too small, and because of a rare disease, while the rest of the body was going to grow, this region was not going to grow. And so that means sooner or later there'll be insufficient air and the child is going to die. So they did this stem cell treatment to regenerate the thorax, okay, the windpipe. And it now turns out that after 2 years, it has grown out to be a living thorax, which can be completely replace the original problem. and now the child has survived for 2 years, and the diagnosis seems to be that that kid is going to grow up to be a normal human, a normal adult. And so that's a major, that's the first major example of in the human being, right, an organ being regrown completely. And so the thing is that maybe with over time you can have more complicated organs be grown over that, and maybe this technology becomes obsolete at that time. But in the interim, maybe this is potentially a solution for the next 10 20 years. That's what we think, if it is successful. I mean, it's still not a completely commercially viable product, but it has received enough investment to try to take it to the next stage of testing it out on animals and human beings. And if it is cleared over, usually in those cases it will be tested on patients who have little other option left to live, and then they'll go from there and build it off from there. Yeah. So a lot of possibilities. You will see from Igor's presentation some ideas related to medical devices. You will see in Sheridal's presentation something about energy storage, and so, and then each of you are going to provide some other examples on catalysis, on structural properties of zirconia synthesis, clay nanoparticles, and some porous structures. Okay. We talked about aluminum nitride. Do you remember what are some interesting properties of aluminum nitride? Yes, so it is electrically resistant but thermally conductive, right? So thermal conductivity is high, electrical conductivity is low, and so you would use that for a package, right? Also, the coefficient of thermal expansion is very low and similar to silicon carbide and silicon materials, and so it is useful for packaging applications. We wanted to try to use nanoscale aluminum nitride mixed with microscale aluminum nitride. So bimodal, right? Large particles, you fit small particles in the middle of them, right? And then you see you increase the packing density. Because microscale aluminum nitride itself only fills to about 52 volume percent of space. Nanoparticles, on the other hand, because of their electrostatic repulsions and agglomeration, they don't fill more than about 40 volume percent of space. So the idea of nanoparticles which pack poorly, increasing the packing density of another powder that packs poorly, hasn't been tried before. Those large spheres and small spheres that I showed to increase, as an example of particle size distribution, increasing packing density that I showed, were for particles that are typically tens of microns and a few microns. For them to be in the nanoscale range, not a whole lot of work has been done before. And so we were able to try to look into that. Work done by one of my students, Valmeganathan, and a couple of other students. Nathan is working with Intel Corporation after finishing his PhD now, since last year. And what he found out was, this is in weight percent, what is the maximum content of the powder in the polymer. Okay. What is plotted here is the ratio of micro to nanoscale particles. So two things you can observe. If you change the ratio of micro to nano, the maximum packing density changes, and it goes to a case of around close to 91 weight percent, which turns out to be close to 72 volume percent. So you had one powder that had a maximum packing density of about 54 volume percent. You filled it with another powder that had a maximum packing density of about 40 volume percent, but the combined mixture in some ratios allowed you to get close to 72 volume percent, which is really high for ceramics. Here is viscosity plotted as a function of solids loading. If packing fraction increases, what did you learn in your when you were dealing with mixtures? What happens when the packing fraction increases? What happens to the viscosity? Now, what about the maximum packing fraction? If that increases, what happens to the viscosity? As it goes up, that phi c increases, and so viscosity actually goes down. And so this is what we saw. This is just the blue beads are just micro scale aluminum nitride, about 0.8 microns aluminum nitride. Now if you fill the space with nanoparticles, you increase the maximum packing fraction. And so for any given packing fraction, you have lower viscosity for the bimodal system. You increase maximum packing fraction, you will reduce the viscosity for any given volume fraction. As you increase the volume fraction, of course, viscosity will increase. So you have two possibilities now. You can either be at the same volume fraction of powder and just get better processability, or you can go all the way up to 72 volume percent, and so you can get much better structures in terms of controlling the dimensions when the material gets sintered. So you can control sintering shrinkage. Appear and press shortly.